Right, so hello everyone and welcome back to another competitive programming video. Today we'll be doing a British Informatics Olympiad question again, the 2012 question 1. Okay, so let's just have a look at the question. So they're basically asking for the distinct prime factorization. So I'm sure that you guys know what prime number is, and the prime factorization is basically just like having the number in its as a product of all its prime factors. So 100 becomes 2 times 2 times 5 times 5. Since this is the only way to get 100, unique way to get 100 from its prime factors. Okay. And we want the distinct prime factorization, i.e. Since this is 2 times 2 times 5 times 5, we don't want the duplicate 2's and duplicate 5. We only want 2 and 5. So, for example, if we had 8, 8 is 2 cubed, but then we would only be interested in 2. And similarly, like 24, 24 is 2 cubed times 3. We wouldn't be interested in the cubed, we would only be interested in 2 and then 3. So it would become 2 times 3, so it would be 6 as the output. And we want to read a number between 1 and a million and outputs the single integer being the distinct prime factors. Okay? So I'll just walk through the initial code. So as you can see above, I have a commented out code. I'll go through this one later. This one's it's much slower, but it goes through the Sieve of Eratosthenes, which is a really important programming concept. And I'll go through this after I go through this main code, which is much faster. This is slower, but it's still like fast enough to pass the test cases, and this logic will be handy for future questions. So this is the original question. So I'm basically just accepting the input, and I have this set. This set, I'll come to why I used a set later, and I'm iterating from 2 to all the way to the number, and this is iterating through all possible potential prime factors of the number. And what I'm doing is, while I is less than or equal to the number, so I am just adding numbers to the set, okay? And these numbers will be the prime factors of this number. So I think it's a bit like unclear if I just explain it like this. So let's just go to the whiteboard and I'll quickly show an example of how exactly this code will work. Okay, so let's say we have the number 8, for example. So what we do is we iterate from, actually, 8 is probably not a great example. Let's pick 24. So we iterate from 2 to 3, 4, etc., all the way to 24. So what we do is we start with 2. Now, is 24 divisible by 2? Yes. So we rewrite 24 as 12, okay? So now we can erase 24 and write it as 12. Now, is 12 divisible by 2? It indeed is. So then we can erase 12, make it 6. Now, is 6 divisible by 24? 6 is also divisible by 2. So we can rewrite, 6 is divisible by 2, so we can rewrite it as 3. Now, 3 is no longer divisible by 24 anymore. It is no longer divisible by 2 anymore, sorry. So now we go to the next number. Now we go to 3. Is 3 divisible by 3? Yes. And now we've basically reached 1. 1 is our base case, and now we just stop. And now let's just have a look at another example quickly. Okay, so let's say we have 50, for example. So we start iterating from 2. Is 2 divisible? Yes. So we rewrite this as 25. Now we go to 3. And now, is 3 divisible? No. So now we go to the next number. 4. Is 4 divisible? No. Now we go to the next number, 5. And now, is 5 divisible? Yes. And now this can be written as 5. Now, is 5 divisible again? It is. And now this can be written as 1. And now, bear in mind, I skipped past this, but it's important. So 4 is not a prime factor, so even if it is divisible, we can't really do anything. However, we're guaranteed not to have 25 divisible by 4, since every number before 4 is made up in 4's prime factorization, right? 4 is made up of 2 and 2. Hence, we've already got rid of all the 2 components of 50 when we went through 50 by 2. So now it will never be divisible by 4 directly, right? So then, likewise, if we take any n, and if we go to 6, 7, 8, 9, 10, 6 isn't prime, 8 is not prime, 9 is also not prime. Hence, these numbers are never going to be divisible by 6, 7, or 9, 6, 8, or 9. They will only be divisible by 2, 3, 5, 7, 11, 13, and so on, all the prime numbers. Okay, now let's just go back to the program and I'll walk you through the rest of it. So this while loop is basically just testing while the number is still divisible by 1, while the number mod I, so while like n mod 2 is still 0, while it's still divisible by 0, we're adding it to the set. This set is the unique prime factors set, and then we are dividing the number by I, and then we're reiterating. We continue this until the number is no longer divisible by I. After this, we increment our iteration counter. So just how we did in the example, we went from 2 and now we're going on to 3. And now if I equals num, for example, if like our iteration is greater than the number, then we basically just break out of the loop since we've basically finished. For example, if our iteration becomes like 6 and our number is only like 4 or whatever, then we're basically finished since we've gone through everything. In my particular example, 6 and 4 will never exist, but since 4 would have already become 1 in whenever it becomes, whenever it goes through 2, right? And as soon as a number has completed its prime factorization, it will become 1, which means that it will always be greater than whatever I we have. And as soon as the I is greater than the number, we'll break out of this while loop. And now this output is basically 1, initializing it to 1. And now for each number inside the set of prime factors, we multiply by output, and then we print the output, okay? So now if we were to print the set, it would be like 2, 5, or whatever. But now if we print the output, it will be it'll be the multiplication of all the numbers inside the set. So if we just test this on some of the sample inputs, if we go here and if we test it on this large number, sorry, I just a bit of a typo there, but there we go. Oh wait, I'm accidentally running a different program, sorry. But this large number, according to us, is going to be 13. So it's unique. This number is basically going to be a power of 13 only, which means it's going to be like 13 to the power n, where n is a like integer basically. So yeah, like this program works, and if we test on the very largest input which they provided, which will be this, as you can see, this outputs in very short time, like less than a few milliseconds. So this is the fast way to do this, but this other approach is also a valid approach, and I'll quickly just go through this one as well. I would recommend that you also listen to this in case you're not familiar with the Sieve of Eratosthenes, since this is a very well-known thing in like the math side of competitive programming, and it's useful for other problems. It's not too useful here, but I'll just walk through this code quickly. So we're initializing the Sieve array. This and it, like I guess I'll just talk you through it a bit. So we iterate through each number, and now if the Sieve of this number is 1, so this basically means that if the number is prime, we initialize all numbers to prime since we haven't found any prime factor of that number yet. I'll come to what this means in a few seconds later, but so if the Sieve is 1, which means that it's prime, we iterate through all multiples of that number. So for j in range, I to the limit, and we're incrementing in step I. So for example, let's say our I is 7, we iterate from 7, 14, 21, etc. And now we basically multiply that sieve of j by I, okay? So like let's say 7, and then when we get to 28, we multiply 28 by 7, since one of the unique prime factors of 28 will be 7. And we're not concerned with how many times 7 goes into 28. So for example, let's say I was 98. Then 98 goes into 7 14 times, which means that 90 is actually 7 squared times 2. But we're only multiplying it by one instance of 7, which is exactly what the question wants. Unique prime factor of 7, right? And now what this does is, for any number which is not a prime number, let's say by the time we get to 4, 4 will not be prime, since whenever we iterated 2, which is less than 4, we would have updated 4 with the value 2 anyway, which means sieve of I will not be 1. So we will not need to iterate through all subsequent numbers. So this logic is called the sieve of Eratosthenes. If you want, feel free to research it a bit more. It's a very interesting and useful side of competitive programming. And if we use this, this will also work for any input, and this will output in a few seconds, which will be a bit slower, but it will be fast enough to pass the test case. So yeah, as you can see, it still worked. So this code is useful for generally in competitive programming, as I've said a couple of times now. And yeah, so these are basically the two different approaches which we have. This approach is probably a bit more intuitive and faster. This approach uses the sieve of Eratosthenes. And that's pretty much it for this question. I hope you enjoyed. I hope you learned something new, whether it be the sieve of Eratosthenes or the original approach we had to solving this problem. And I hope to see you in another question another time. Thank you very much for watching this video, and goodbye.